Even when there's no current graphics, so most of the houses. Anyway, they're professionals. They're supposed to yeah, we didn't have any furniture. The ball up here. Oh, that's good.
Do I need to restart it? Who can help? Yeah.
Not really much. How many firsts does it take to turn on the
Maybe back out of this program. Can you exit out of this program?
Yes. This activity file. Do I need to restart it? Unplug this.
I just did that. Okay. Now try it out.
How many chairs does it take to turn on?
We're doing screening from undergrad. You don't do it in that keeps up with it. Embarrass yourself.
Okay, good.
But it's in Chinese. Oh, well.
Okay.
Okay.
Excellent. All right. Thank you for coming. I am happy, very happy today, not because it's the last day of classes, but because I get to introduce to you today our own Professor Yang-Shi Wu. When I arrived here, not so long ago, I got to meet Yang-Shi, who I came to learn was working on really cool stuff, quantum field theory, particle physics, stringy things, fundamental physics. And I learned only later that Yang-Shi had this whole other side to him. He had crossed over in that really, really slippery way that you do with quantum field theory, where you take the time and let it go imaginary and backwards, and you end up in the condensed matter world. And today, we will talk about his research in the area of topological phase transitions, which led to the award of the 2016 Nobel Prize in Physics to 3 physicists, 2 of whom were collaborators of Yang-Shi's. So without further ado, we'll hear about the other fundamental physics from Yang-Shi.
Yeah. I did not do a colloquium actually for quite a number of years. Yeah. Previously, yeah, when I first came here, a few years, I would like to make one colloquium. Today, yeah, I'm very happy to talk about the making of 2006 Nobel Prize in Physics. The title is When Topology Meets Many-Body Physics. Here I use meets because these memories were very vivid to me. Also, I emphasize many-body physics here because actually topology first appears in particle physics. But however, the achievement for the with using topology actually has been much bigger in many-body physics. So this is Nobel Prize page. I believe many of you have looked at this already. So this David Zaulas, he was awarded with half, and the other half was shared by Duncan Hordern and also Mike Kastelitz. I was fortunate, to have collaboration with these two in early or middle 90s. That was beginning of topological investigations in condensed matter physics. So by the end of the talk, I will talk about some stories of my personal experience with both David and also Duncan. So this is outline, a lot of issues, but however, I will try to make my colloquium in terms of simple words and pictures rather than equations or details of physics. So first, of course, is what's topology. When I first heard the term topology, it was in high school. To my knowledge at that time, I thought topology would be similar to number theory, namely it would have nothing to do with physics. Things are abstract and hard to understand. And however, as we will see that actually in last century, especially in last half century, topology really help physics a lot in understanding the physical world around us. These are three things actually were brought to the press conference held by the professor who announced it. So here we are looking at the surface of these three things. We notice that they look different. But however, the difference between these three actually is very profound. So, namely, they have some important, very crucial difference between their topology, even if we, do the continuous deformation of the surface. For example, we may make a dent, for example, on the surface of the orange, or like this diagram. We have, so the mark actually has the same topology as the torus. So first, by definition, topology studies properties under continuous deformations. But however, mathematically, actually, it's very difficult, at least as the beginning, to describe and characterize the topological difference between these things. Although intuitively we say, okay, the surface here has no handle. The mark here has one handle. This actually has two handles. But however, these things are just qualitative. Namely, we cannot easily describe mathematically the difference here. Oh, sorry. Here we have three handles. Okay. So the important thing is how to describe and characterize topological differences between, for example, these three things. Historically, topology actually started with Euler, a Swiss and Russian mathematician. So, for example, he notes that, if we consider plahedron, we count the number of vertices, for example, for the tetrahedron is 4. Number of edges is 6. Faces, 4. Then we construct the Euler characteristic, which is V minus E plus F is equal to 2. Then you can see that for all regular prohedron, this number is always 2. So the Euler characteristic is defined by this sum. It's a constant only depending on 2D surface. So for the surface of any convex or spherical polyhedron, this number is always 2. So this is a kind of combinatoric, but later Gauss discovered that actually the Euler characteristic, for example, for a closed surface, can be written as an integral like this. Surface integral of the integrand is so-called Gaussian curvature. Okay, so when we do continuous deformation, locally the Gaussian curvature can change, but however the integral over the whole surface of A actually is constant, does not depend on the continuous deformation. And also, we have the equality that Euler characteristic for a closed surface is twice 1 minus g. G is nothing but the number of handles. Okay. So, for example, now mathematically we can distinguish between these three. We say sphere has g equal to 0, torus g equal to 1, and pretzel g equal to 3, and so on. Okay. Also, for physicists or mathematicians, we are happy. There is an integral which we can do. Okay. Yeah. It's easier than to guess a combination of numbers to get a topological invariant. Later, in the history of topology, one thing is interesting is the so-called Wending number. When we consider contour integral in complex analysis, for example, we want to know how many times this contour C, goes around a fixed point P. So in this case, we know it's 2. But actually, this number can be expressed as the Wending number for a map from S1 to S1. Namely, we start from a small circle around P. Then we map the point on C to the point on the small circle, okay, intersect by the straight line. So then we can see that this Wending number is always an integer, which can be expressed in terms of this simple integral. And this Wending number actually is a topological invariant if we do not allow the curve C, go through point P. It's a topological invariant, even if we can deform C in many different ways. Another Wending number is, for example, from map S2 to S2, two-dimensional sphere to two-dimensional sphere. So we can express the point on a sphere using the so-called stereographic map. And so we have a point P on the sphere and P prime on the plane. Therefore, the winding number W21 now, if we do a rotation on the sphere, it becomes this way. But however, the winding number actually is same even under such a mass. Usually in condensed matter physics, we like to, for example, express spin configurations on a plane in this way. Then we can see that the spin configuration, this guy and that guy actually has the same winding number. If we use a unit three-dimensional vector to denote a point on the S2 on two-dimensional sphere, the winding number here actually can be expressed in terms of this integral. In 1940s of last century, a Chinese mathematician, Xinxin Chen, actually generalized the Gauss-Bonnet theorem. First, he presented an intrinsic proof, namely the proof is independent of the embedding of a two-dimensional surface in 3 dimensions. Later, he and the other mathematicians generalized the Gauss-Bonnet theorem to higher dimensional Riemannian manifold. Finally, he were able to generalize to the so-called favorable bundles, which actually are mathematical equivalent or counterpart of gauge theory in mathematics. Namely, the gauge potential in physics actually correspond to connections in physics, especially geometric curvature, which appears in the Gauss-Bonnet theorem, actually corresponds to field strengths. Then we can easily use the gauge theory language actually to formulate Chen number or the Chen-Simons form. For example, if we consider one-dimensional integral, Chen-Simons one form actually just gives us the line integral of the vector potential, which may be used to describe the so-called Aharonov-Bohm effect. Also, the surface integral of the B field or the magnetic field actually gives us the so-called first number, which in electromagnetics electromagnetism corresponds to magnetic charge. The Chen-Simons is a three-dimensional integral. Okay, so which gives a term in the action which defines a gauge theory in 3 dimensions is called the Chen-Simons term. So A here is gauge potential, F here is field strength. In 4 dimensions, actually, we have a 4-dimensional integral of this quantity, and it's a topological term called the theta term in 4-dimensional gauge theory. So Chen numbers first appears in gauge theory. Now, I will begin to discuss how these things are related to physics, especially many-body physics. So the first thing is the topological phase transition in thin films. We know that in the physical world around us, there are the phenomena of involving crystal ferromagnets, and also in laboratory we have superconductor. According to Landau, he discovered that the so-called continuous phase transition between, for example, crystal and vapor, or the ferromagnet versus the paramagnets, or the ordinary matter superconductor. These new ordered phase are due to the so-called symmetry breaking. In the crystal case, it's translation symmetry, continuous translation symmetry is broken to discrete symmetry. For ferromagnets, it's the spin rotation symmetry is broken. For the superconductor case, it's the U1 gauge theory, which is broken. So the symmetry breaking can be described in this way. For example, if we consider the superfluid case, in that case, the order parameter is a complex field. So the complex field has a potential energy, which has a form of a maximum hat. Then we can see that, the system does not have the lowest potential energy at the origin. Actually, it has lowest potential energy at the bottom, which is a circle. Actually, this potential exists at each point of space. So the ground state of the field system actually is a mean value of phi equal to 0 everywhere in space. And this breaks the phase. Not equal to 0. Not equal to 0. Phi here, not equal to 0. Then this breaks the phase symmetry of the complex field and the potential. Okay. Then what's interesting is that around the ground state, there could be two modes. One mode is in the radial direction, which is the well-known Higgs mode. Also, there are Nambu-Goldstone modes, which makes the phi field go along the direction of the bottom circle. However, it turns out that in two-dimensional space, the fluctuation of the Nambu-Goldstone mode actually give rise to divergences. So this divergences, appearance of this divergence is interpreted as Wagner-Mermin theorem in 1964. Namely, there is no spontaneous symmetry breaking phase transition of continuous symmetry in D less than 2. Then it was claimed that according to this theorem, superfluid phase would not exist in the form in a thin film. Okay. However, a violation of this theorem was discovered later. So actually, it was because of Belyansky, Kosteles, and Zaulas. They have noticed that in two-dimensional, so here is a vortex in 3 dimensions. In 2 dimensions, for example, for superfluid field or for magnetic field, so-called XY model, in which the magnetic moments all lie in the same plane. Okay, there are vortex solutions. Usually, these solutions are called as topological soliton because the winding number of vorticity here is quantized. The existence of this kind of topological solitons actually changes the picture about the phase transition. At, for example, very high temperature, high temperatures, we may have many single vortices. They are free. We have vortices or anti-vortices, okay? However, if we consider a pair of vortices, vortex and anti-vortex, actually they are weak interactions between them, okay? So when the temperature drops down, the kinetic energy of the vortices becomes low, then the attraction of between a vortex and anti-vortex pair becomes important. So after certain critical temperature, actually all vortices becomes vortex and anti-vortex tidal pairs. So therefore, a phase transition between a thin film with free vortices and a condensation of bounded vortex anti-vortex pairs actually give rise to a phase transition. This is the so-called Belyansky, Kosteles, Zaulas transition. I put a bracket here because in many literature, this phase transition is only called the Kosteles, Zaulas transition. I didn't search much of the literature. Maybe later Oleg can talk about the contribution of Belyansky, okay, who unfortunately died in 70s or 1980s. I mean, yeah. Okay. So actually, the Kosteles-Zaulas theory later was verified by experiments. For example, in this diagram, this is the straight lines prediction of the Kosteles-Zaulas theory. And these are experimental points about critical temperature dependence of the so-called superfluid density. Okay. In recent years, even in the cold atom, okay, gas, actually the KT phase transition can be realized. So the importance of this transition is that it's a condensation involving topological solitons. So the behavior after the condensation actually is very different from the usual phase transition in 3 dimensions due to spontaneous interbreeding. So this also is a very good example. Tell us that there is new physics in lower dimensions. When I first heard of this, it was in the 70s. I was in the Institute of Physics in Beijing. And at that time, my background was still particle physics. Then I feel, wow, originally I thought lower dimensions should be simpler because as particle physicists, we were thinking about the closed Klein theory. We need to go to higher dimensions. But however, this tells us that in lower dimension, they are also very interesting physics. Also, this began to draw the what's wrong? Okay, yeah, attention of condensed matter physics, in general theoretical physics, to lower dimensions. Now, let me talk about the hold-on phase. In an ferromagnet spin-1 chain. So this is the Hamiltonian for the nearest neighbor spin-spin interactions. And when J is greater than 0, we know that the ground state is anti-ferromagnets, namely spin orientation actually alternates along the chain. Here we assume these spins are operators or matrices. They satisfy the usual angular momentum commutation relation. In general, the spin can be S, okay, for any number of S. Of course, we assume that every lattice site has a spin S. So it turns out that, this chain is very interesting because originally we thought in a magnetic chain the excitations should be the so-called magnons, especially for the ferromagnets case is magnon. But however, in the anti-ferromagnet case for spin 1/2, actually, suppose here we have a domain wall. Later, we can see that this one magnon actually is split into 2 spin lines, move in different directions. This is the Ising case. For the Heisenberg case, the domain wall here is not sharp. We have some, region in which we have the transition from this domain to that domain. Again, here we have a split of one magnon into 2 spin lines. This effect is important in recent study of topological physics. Namely, we can have the so-called fractionalized quasi-particles. Previously, before Holden's 1983 paper, people thought that all spin chain with any possible spin S should be gapless because the excitation spectrum for spin 1/2, which has been exactly solved by Bate in 1931. Later, Anderson considered S tends to infinity case. He also got a gapless phase. So then people think, okay, this end is gapless. The other end is also gapless. So for every spin, the system should be gapless. Nobody challenged this idea until Holden. Holden then argued that for S equal to 1 spin chain, actually at this point, Q equal to pi, there is a gap. For this sounds, simple, gapless and gapful, who cares? But in condensed matter physics, we know that that's very important, okay? Gapless and gapful, especially for low temperature physics. Gapless system and gapful system, have very different behavior. Okay. So later, there were many studies, either numerical or construct some model which are in the same universality class and exactly solve those models. Even up to now, there does not exist exact solution for anti-ferromagnetic Heisenberg spin wind chain. Okay? But however, there are some other spin wind chain which is not exactly Heisenberg, which can be exactly solved. It turns out, indeed, the spin wind chain can have some interesting ground state. So here, this is a chain. So spin one at each side. However, we can have a pattern construction, namely each spin one here actually consists of 2 spin one halves. Then we can have entangled state, singlet bonds between the partons on the neighboring side. Okay, then we project each side, 2 spin one halves into a spin 1 particle. So this is an entangled state. Okay, it turns out that this model actually is in the same universality class of the anti-ferromagnetic Heisenberg spin wind chain, or same as the Holden state. So such state in physics is called a valence bond solid, which is very different from the spin one half case. Also, the effective field theory for the anti-ferromagnetic spin wind chain, actually for any anti-ferromagnetic, the path integral plus continuum limit actually give us a nonlinear sigma model in 2 dimensions. However, there is a possible topological term. You can see that the integral here is nothing but the winding number from S2 to S2 I have talked about. Then in path integral, it turned out that when we exponential this term, we can see that if the spin is 1/2, we get -1. If S equal to 1, this term actually gives us 1. 1 means there's no contribution to path integral. So indeed, there is a qualitative, very profound qualitative difference between spin 1/2 and spin wind chain. And also because a topological term actually is involved for the effective field theory. So now the state or the phase, the Holden phase, is called a symmetry protected topological these are, I believe, neutron scattering data to show the existence of the Houghton gap. Oh, sorry. Diagram here, yeah, it's not show up. Anyway, it again shows the existence of the Houghton gap. Okay, just believe me. Okay, now let us talk about the quantize Hall conductivity as topological observables. This actually starts in 1981. I mean the new wave for or the starting point of the study of topological matter or topological physics. Fractional quantum Hall system is a super clean two-dimensional electron system at a low temperature and in strong E field. Hall effect means that if we impose a voltage in this direction, electron would move this way, and however there is a Hall voltage in the transverse direction, then we can define the so-called Hall conductivity. It turns out that this is the experimental curve for the Hall resistance. Then you can see that there are plateaus. Okay, the existence of these plateaus happens. The value actually is given by an integer or a fraction of E squared over H. The suppression feature of this effect is that the flatness or the extremely high precision of, for example, for the integer quantum Hall effect. It turns out that the R from Clayton, actually, you can see it can be measured in terms of almost 12 digits. That's very precise. But this happens in a condensed matter system. Why the natural value can be so precise? When I was young, I did not like condensed matter physics. At that time, I thought condensed matter systems are dirty. And I like particle physics. Particle physics is clean, I thought. Okay, so when I first learned this was in Stony Brook in summer of '81. Professor Xin Yang, gave me a reprint of von Clayton paper. He said that you should, pay attention to this paper. It will be very interesting. So later, when I came to Seattle, I will tell the story. Okay, I began to learn about the physics of this. So actually, it was. Sorry, I forgot the reference. That's Saulus and his postdocs. 4 people wrote a paper to explain why the plateau value of the Hall conductance or conductivity is very precisely an integer, because it's a topological invariant. It's related to a first number. So first number is related to a gauge field. But in this case, the gauge field is not in the real space. It has nothing. It's actually a gauge field in momentum space. And the integral here should be done on the Brane zone of the bands. If the Fermi energy fill a number of bands, so a completely filled band, if we compute the field strength of this gauge field in momentum space, we get the Hall conductance. Okay. So here, U here, I would like to mention this U here actually is so-called block function, okay, which is the solution of the Schrödinger equation in a crystal for a purely periodic system, non-interacting electrons. However, we know that the real system actually did not correspond to non-interacting electrons in periodic potential. So, although this paper, said the first word about the nature of the Hall conductance in a toy model at that time, okay, it did not correspond to reality. But the question still exists: why for real system this is still true? And this final word about the quantized Hall conductance as a topological invariant was said in this paper. Before this paper in the literature, there were many papers trying to generalize, the original TKN's argument to different systems. But however, in this paper, actually, we consider a very general system. We do not need the existence of periodic potential. Also, for example, we allow impurities. Also, the electrons can have interactions. Then we prove that the Hall conductance is still a topological invariant. So our trick there is to introduce two periodic parameters for a two-dimensional system on a torus. We can insert a magnetic flux through a hole of the torus. The torus actually has two holes, so actually we can have two flux. The existence of this flux actually gives us the sort of trace boundary conditions. So for a lattice diagram, let us try to identify this side with this side. So they are hopping from here to here, which actually geometrically correspond to hopping from here to here. But however, we require the hopping amplitude for these two, identified two. Actually, they may differ by phase factor. So the periodic boundary condition is generalized to trace boundary condition. Then the Hamiltonian plus these trace boundary conditions becomes a system with two periodic parameters. Then we can play the same game as TKN. In his case, it's the Brane zone. That are case in Brane zone are periodic angular variables. But here we have these two trace faces. Okay, so then the integral of the field strength, B field, in this trace phase space give us an integer. This integer actually is related to the averaged whole conductance for the system. So in this way, the topological nature of the sigma xy, I mean the whole quantized whole conductance is verified. Later, especially in recent years, this trick, namely impose the trace boundary conditions, becomes a very important one in numerically check whether a system is in topological physics or not. If the system responds to the trace boundary conditions, but still the integral, the topological number is an integer, then the system is in the topological phase. Okay, so of course, Thouless and Jordan, they have many other important contributions, not cited by the Nobel Prize. But however, I will not go into those details. So I would like to talk about some small stories of my experience and collaborations with Thouless and Jordan. I may put this photo over there, but then it does not look good because they are different directions. So I intentionally exchanged it. Okay. Later, my work. Okay. First, about Thouless. I first came to the U.S. To Stony Brook. At that time, Professor Xin Yang was the director of the Institute for Theoretical Physics, which now is named after him, the Xin Yang Institute for Theoretical Physics at the Stony Brook. Later, I went to Institute for Advanced Study at Princeton for 1 year. There, at that time, nobody was working on the quantum Hall effect. So then, in summer of '82, I got a job offer in Seattle. At that time, I did not know actually Thouless was there, but however, I forgot. It may be the second or third colloquium was his. Then I was very happy because I remember Professor Yang's advice. I knew his talk was about the integer, exactly the TKN number and so on. The first semester, I was in a different floor with a particle group. Later, one semester, I moved my office to the group of particle theory group. What's interesting is that the particle theory group there share a very big room with Thouless group. The structure is similar to our NSCC. NSCC has 2 entrances, okay? But however, in Seattle, there was only 1 entrance. So we were at, different places, but however, each day we met the people. Especially, Thouless at that time has, what happened? No, I don't know what to do. I cannot see my arrow.
It's on the screen.
Where?
the screen.
Look behind you.
Okay. It's not here. Okay. Yeah. Zaulus has one Chinese postdoc and one Chinese student. So they first came to me, asked me questions and so on. So then I have a lot of discussions first with Zaulus postdoc and his student. We began to write some paper. However, one day Zaulus was away to England. His student knew in Chinese here is not Kun, it's Chen. Okay, Chen Niu. Discuss with me. I learned a lot from him. Then suddenly, the possibility of trace boundary conditions, came to my mind because I know that in some lattice gauge theory people, they try these things at that time or before. Then I thought, okay, yeah, we have two periodic angular variables. Why we cannot repeat? So I knew at that time actually becomes very familiar with these things. Then after Zaulus' return, we discussed in the new, first did the drafts and so on, and this paper came out. At the beginning, I felt that, Zaulus, as in English, gentleman, sometimes looks very serious. So at the beginning, I did not dare to talk to him according to Chinese tradition. Okay, but later, after that discussion, of course, I feel that he has been easy to contact or to access. So later, we have a collaborative paper in addition to this one. This one was quoted both by the Nobel Prize Foundation, also by APS journal. Okay. Also, Zaulus is a very good physicist in the following sense. At that time, he was working on fractional quantum Hall effect, not integer quantum Hall effect. At that time, Laughlin's paper was out already. But however, the Chinese postdoc of Zaulus had a different theory, which now is called the Tau-Zaulus state, which is not it's not a quantum incompressible fluid. It's a sort of Wigner lattice. Okay, numerically, actually, these two states are competing. So his postdoc actually wanted to push, this paper out very much. After a few months or half a year, Zaulus agreed. So Tau-Zaulus paper published. Then 1 year later, Zaulus wrote a paper and published, saying that Tau-Zaulus was wrong. Tau-Zaulus paper was wrong. Okay, then it's like a bomb in the physics department because Zaulus, had been so famous in the condensed matter community, right? People, saying that, okay, similar phenomenon actually had happened many times, when new experiments came out, many competing papers, many papers could be wrong, right? But nobody came out say, I have been wrong. Rather, but Zaulis wrote that paper saying that he thought about this problem for a long time. Finally, he was convinced himself that he had been wrong. Okay, this is a very interesting story. Also about Holden. I came to know Holden in Aspen. That's in the summer of '84. Okay, that was my first time to Aspen. Then one day, Holden came to me, saying that, please come to my office. Then I went to his office. On the deck, there are many pieces of paper with numerical results. At that time, he was doing numerical computation for fractional quantum Hall effect on his field. He showed me, okay, there is an obvious gap for quantum Hall, fractional quantum Hall system on our sphere. And he had known, I guess, Zaulis postdoc Tao and I had published, not really published, only in reprint, a paper claiming that fractional quantum Hall system should have degenerate ground states. So then at that time I had a topological argument. Up to now, it was still correct, okay? But at that time, Holden did not believe in me. He showed me so many, diagrams. Every diagram there is an obvious. Then I told him that, okay, I agree with your thing, but your thing is on a sphere. To see the ground state degeneracy, we need at least a cylindric topology or a torus topology. At that time, there was no idea of topological degeneracies. Even us, we believe we use a spectral flow argument to argue for the ground state degeneracy. We still thought it might be related to symmetry breaking. Now we know this actually was wrong. It was not due to symmetry breaking. So in that afternoon, actually, we could not convince the other, okay? Yeah. But after that, okay, we became very good friends. Then 85, I met Holden again in Aspen. He and I discussed about physics of the so-called fractional statistics, and we wrote a joint paper and published in PRL. Okay, that story is related to the so-called alien statistics or fractional statistics in 2 dimensions. This was my PRL paper. Just after my interview in Salt Lake City. In this paper, actually, I consider the effect of the complicated topology of convex space for indistinguishable particles in 2 dimensions using the Feynman path integral formulation. I claim that it allows exotic statistics. Actually, Frank Wilczek had the alien model already, a charge combined with a magnetic flux, and he claimed that this Aharonov-Bohm effect can be interpreted as fractional statistics. But however, for that construction, 2 anyons is the easy case. However, if we consider 3 anyons, it becomes more complicated and so on. But the path integral actually solves that problem. So then it turns out that in 2-dimensional space, the group which is responsible for the anyon statistics or exotic statistics is the braid group. Okay, braid group actually is related to usual permutation group. For usual permutation group, if we do a permutation of 2 things twice, we get an identity. If we drop this, actually the permutation group becomes the braid group. So then I think here there's first Zaulas, came to me. He was interested in this possibility of new physics because some people, I think it's Professor Halprin at Harvard, already proposed this kind of statistic, maybe related to fractional Cohen-Maui effect. So then, we discuss about spin statistics of clusters, invariant characterization of statistics, and the effect of space topology on these things. Then, we have this paper published. Then, as I've mentioned, in the summer of '85, both Jordan and I were in Aspen again. So Jordan was also interested in the fractional statistics. Then we want to see whether the fractional statistic can appear in the superfluid. Normally, superfluid is compressible, so we rule out this case. So this means physically the anyon statistics can only happen for a gapful system. For compressible fluids, it's a gapless system. Okay, so this is a necessary condition for the appearance of the anyons. Okay, so while I was preparing this colloquium, then I remember, this is the transparency of my interview talk. I remember, that was in May of '84, and Professor Carton actually met me in the airport. Okay, and so at that time I talked about new ideas in theoretical physics from topological investigations. This is the first page. Then there's the last page, the conclusions. Okay, I emphasize that in particle physics, up to that time, probably it's also true. No positive experimental evidence for topological solitons. Perhaps, except the chiral solitons. Okay, but anyway, magnetic monopole have not been verified by experiment. Also, cosmic string as a candidate of topological solitons, has not been observed. But in condensed matter, at that time, I say evidence is encouraging. But now, of course, it profits. Okay, so apply. So in this retrospect, we can see that there are close relationship between topology and quantum matter, topology and quantum entanglement from the wave function of Holden state. Okay. Later, this the quantum entanglement in a topological state actually is a very hot topic. Also, close relationship between topology and quantum information theory and quantum computation. Topology may also be relevant to the sort of emergent space-time or emergent gravity. What's interesting is that topology and geometry, especially topology, actually is a branch of science which actually joining mathematics, physics, and information science into the so-called topological quantum computation. So, yeah, one of my dreams, I hope, but I'm not sure, okay, I can live up to the day to see, the realization of topological quantum computation. Okay, thank you very much. Using anions, I forgot. Using anions.
Unfortunately,